and take the square root inverse, you get the speed of light. Well, it's even built in to just these basic relationships. So I just kind of threw it out there and said, oh, you multiply these things, we can measure them in the lab, which is pretty surprising when you think about it in terms of light. But foundationally, it's just sitting there, right in the middle of the first two or the first three of these electromagnetic equations. So it's kind of interesting, it's kind of cool. So anyway, I just sort of put this together just to kind of compile some ideas that I'm not going to test you on this per se. But I think aesthetically it's a pretty profound idea. And the other thing that I put, if you look on the second and third pages of this, was just sort of a completion of, or maybe a re-summary of what we talked about with Gauss's law and mass. And to sort of lay this idea out is that the fundamental nature of Gauss's law is not purely an electric charge, electric field idea. It's the idea that anytime you have a vector field, a radial vector field that's associated with some source quantity, charge, electric field, mass, gravitational field, Higgs particle, Higgs field, strong, I say this, hadron, strong nuclear field. Gauss's law applies as a basic construct for calculations and formulation. So again, there's just a lot of fundamental stuff here that is, in your particular direction, may or not completely pique a deep guiding interest, but I always just kind of feel remiss not to point out some of these interesting little quirks. And when you see a lot of the NOVA episodes on quantum physics or string theory, or whatever the hell they're talking about now, just understand that a lot of these ideas are literally built into their methodologies and their mathematics, surprisingly. So there's a lot of interesting stuff here. But also note the gravity, because you can apply Gauss's law, if you will, is the biggest pain in the ass in physics. Because it sits right in a basic formalism for everything else. In fact, our formalism was in some ways sort of established from gravity originally. Yet, for whatever reason, because of the nature and the magnitudes of the interaction, the gravitational force doesn't fit in the master equation. Hence, they've been spending 40, 50 years trying to figure out how the hell gravity fits in. Oh, let's throw some strings and let's make everything a 100-dimensional universe, and then it all works, right? I mean, that's fundamentally an issue, right? It's what you do when gravity seems to fit every damn thing else, yet it doesn't at the same time. It's like, what do? I don't know. You just make things up and hope it works. We've been doing that since the 1900s. Okay, so the corollary to this, and the direction we're going to go today, is a really cool experiment. I'm not sure if everything is in your kits, per se. Some of it's out here. But, so, the idea is functionally this. One of the fundamental, I should say, applications of magnetic force and electric current interaction with magnetic fields is the ability to construct electric engines or electric motors, which is a very cool technological discovery. And the idea basically goes something like this. If you take a closed loop of wire, and I'll just make it a nice simple loop, and I'm going to fix it on one side just so that it's capable of rotating, but not necessarily translationally moving. And you run a current through this thing. If you run a current through this thing, what happens? The charge.
Magnetic field.
It generates a magnetic field. And the direction of that magnetic field, say the current flows this way, and I guess we could just say it's a loop like this, but maybe it's got a power supply that draws it in. Magnetic field would be finger in the direction of the current, so if we just use the outside, it would be an upward magnetic field this way, which is functionally it's like a bar magnet. Just the presence of a looped current or a loop current carrying wire will generate a simple version of a bar magnet. We refer to the dimensions associated with generating a current this way or generating a magnetic field due to the presence of a closed loop. It doesn't necessarily have to be closed, but it's usually the easiest way to look at it. You just have to have current flowing. We define what's called a magnetic moment. And a magnetic moment, kind of like a dipole moment, but it's different. What it defines is the capability of generating, if you will, in a sense, a simple magnet from a loop of current. And that magnetic moment as a vector is basically related to the amount of current that flows through some surface area, right? The more you condense or expand this surface or this area, enclosed area on this loop, the more you will change essentially the properties of this magnet. And if you have coils or more than one loop, then we can throw this sucker in there, and we can use the right-hand rule to figure out what direction this thing is going, or what direction it's pointing. Now, as we tie this together, and by the way, this is the equivalent of, say, a little spinning top inside of an atom spinning around in the form of, say, an electron. So when we talk about, or if you've ever heard of the magnetic moment for an electron due to the electron spin, usually it's talked about, but you wouldn't see much of it at 200 level force. They're referring to this dynamic. Moving charge generates this magnetic field, which is like a little bar magnet, and a point based on the orientation of the direction of the flow of the charge. So now, here's the thing. When you put a magnet inside another, or next to another magnet or another magnetic field, what happens? What happens to a compass? Yeah, the compass will align itself in the direction of the magnetic field. Or, more specifically, it will align itself so that its north pole will attract to the south pole of the magnetic field that it's interacting with. What's actually happening is, remember, magnetic fields extend outward, and normally when we talk about magnetic fields, we talk about going from north to south outside the magnet, but inside the magnet it's really going from south to north. So it's like a continuous looping field. So when you think about a bar magnet, or you think about a magnet, a loop of wire creating a magnetic field, the direction of the magnetic moment is the direction of the magnetic field inside, not outside the bar magnet.
Could you break that down? Direction of the magnetic moment? What do you mean by that?
Oh, you missed that 5 minutes, didn't you?
I did, I guess. My bad.
Should I? Okay. Take a current, or take a wire, loop it, run a current through it. It'll generate a magnetic field. Inside that magnetic field will point perpendicular to the face of that wire loop, and the direction of that field will be established. Well, we can measure it or define it by the right-hand rule in terms of the direction of the current. The magnetic moment is just a way of describing the relationship between the wire and the area over which the wire extends in space. surface area, if you will. It's related, but kind of looks like a magnetic flux in a sense, but it really isn't, because it's a current times an area, not a field times an area. Oh, and I knew there was something weird. That should be a little hat, right? So you got a little bar magnet, and it's gonna, and if you put another magnetic field around it, then it's gonna point itself and direct itself in the direction of that magnetic field, or it's gonna be altered by the direction of that magnetic field. So say we ran a magnetic field, and just for consistency, we ran it this direction, which should be north to south, right? Outside the bar magnet. So this is external magnetic field. So in other words, it's not the magnetic field produced by the wire, it's an additional magnetic field. Well, two things are going to happen, right? Because you've got current in a wire interacting with a magnetic field, you're going to have magnetic force. If it's fixed so that it can't move, but is capable of rotating, then the manifestation or the presence of that magnetic force will produce a magnetic torque. So if we have an angle between the magnetic field produced and, if you will, think of it one of two ways, either the normal surface area vector, the A vector, if you will, or if you think about it as the direction of the magnetic field produced by the loop. Either way you look at it, the interaction with the sides, with all of these wires that have current carrying them, and their generated magnetic force, will generate torque. The amount of torque we can measure for each of these sides. What would be the direction of the magnetic field on this outer face? We've got a field pointing this way, and we've got a current running this way. What would be the direction of the magnetic force?
Out of the board, away from center.
It's going to be away from center, either out or in. So the force, and we change colors here. The force ought to be looking something like this. Would be like that.
Is that not out of the board?
Yes, it is out of the board. I'm just trying to draw it in perspective to.
I know, I'm trying to figure out this external field, what sort of plane it's in, if it's in.
It's just at some angle. Think of it.
But is it in the plane of the board at that angle? Or are we imagining it just completely skewed?
Well, plane in the board, but it would go this way, right? I mean, it would be pointing along the plane of the board, but it would be three-dimensional in space.
Right.
Yeah. But yeah, I just, for simplicity, keep it in the plane of the board.
Yeah.
So, what about the directions on the sides?
Looks like the one.
Say,
in the
let's
right
just
hand
pick a
would be
side here.
pointing
You've
to
got
the
a
right.
current running this direction.
It'll be going
To the right.
force will be coming to the right. So it's on the outside.
It'd be pointing this way.
Keep this.
Yeah,
Going straight out, right?
Straight out from a 90-degree angle, straight out from.
Yeah. But it's the same sense.
And
Yeah,
then,
so put your hand on
guess we could write it this way.
it. Goes up here, and up there.
I know, the camera right hand rule is fun, isn't it?
Well, so you said,
Well, if you've got the current pointing this direction,
right,
and the field going
uh,
up this way, it's gonna be pointing into the board. And that's So I've got it kind of tipped a little bit, just to
Yeah.
make it a little bit easier to see.
So you said which way is the current?
Current's going.
Well,
that
it's
way.
going this way, so it would be going this way,
Put your palm
inward
like
up on
that,
top.
Right, palm like that, finger straight up for the, something like that.
Finger in the direction of the current. We gotta figure out how to get, I have to tip my hand over to get this in the direction of the field, and my thumb is going out. It'd be nice if it was a 90-degree angle, but I wasn't so kind.
Oh, that is a
So this is a 90-degree angle. I'm trying to keep all this stuff at 90-degree angles. Okay, it's hard to see, it's hard to visualize. But by analogy, the opposite direction would be the force this way. So as we look at it, in this particular plane, what could we say about it? The forces should be equal and opposite. Now the way you calculate the force is I times L times B. But all of the forces are, they're pointing opposite of each other. So not only are their magnitudes equal, as long as this thing is a nice piece of shape. We got another problem. Not another problem, but nothing's really going on. It's an equilibrium. What if we altered the orientation and put the field coming out of the point? Yeah.
So,
So
like that.
see if we can do this.
So basically, how that bottom force is.
So we'll keep the same loop. So hard to see these things. We've got I, and this is tip sideways. Best way I can do it is to take a piece of paper. It's like this. All right, it can rotate this way, but it's sitting like this. So the current on the outer face is doing this. Okay. But now let's move the field out this way so that it's perpendicular. At least one component is perpendicular to the z direction, if you will, but it's got a y component as well. I know, Colonel, we'll get to
So, it's going
so
90 from
it
flat.
would be something like, how do you draw that?
You have to put it like that. It's coming straight out.
I don't want to draw this to you, help me out here. I want it to come out this way. This is out of the board. I want it to come out like this, but how do you make it so that it looks like that?
So you just need your,
I can't draw in this third dimension like
all you
this,
need
so
to
I'm.
do is like, if it's coming out this way, and you think that, I guess, I don't know, that's like that way.
Yeah.
So it needs to be something in,
The-
not a
the little
90-degree
box that you
angle.
mark it with is what gives it away.
Yeah, so here's the area of the magnetic moment. And this is your north, and this is your south. So how, I want it coming out this way though, not this way, this way.
Why is it pointing that way?
Oh, we're all screwed up.
Oh, no.
We're all
If you
kind of
want it like
screwed
this
right
way,
I hate drawing these damn things.
All right, let's
The worst
just-
part of all of
Yeah,
this. My
we'll
stick figures break down.
now. Let's use some pieces of paper, man. Just use a piece of paper a couple of times.
Okay, I'm gonna have to. I'm gonna have to, okay, so take your paper out here, 'cause I can't draw the SOB. I gotta do it this way, okay? So here's your loop of wire. And you've got a field coming out this way.
There's gotta be a video for this,
Right?
Someone get a
right?
picture of
Come
it.
on, look.
Now, what is the direction of the magnetic forces?
Crazy.
What are the directions of the magnetic forces?
You want that one more time? No, I get it.
Current's doing this, right?
So it's going. They're gonna be
So at this angle there, you know, if I just drew it out this way, life would be good.
They're gonna be straight out still. They'll be altered down, right?
Let's just make it 90 degrees this way. So it's coming out of the board. So now we'll make the magnetic field here. Gonna have to do it this way, because there's no damn way I can do it.
So it's flat to the surface.
Flat to the surface. Okay? So it's parallel to the surface, it's coming in this way. Apologize for my lack of
All right.
Okay, so we've still got the wire this way. It's important to get this right so that you can see this. Again, it can rotate along this axis here.
So on the front portion of the wire, the force would be down.
So where would the force be over here?
So
Gonna be up or down?
straight down would be.
That's gotta be according to the plane of this, and the plane of this is gonna put it straight
We
down.
got, right hand rule like this,
Force out, down.
so.
It would be this direction, right? 90 degrees to that. That's what I'm trying to get to.
So it's just like,
B.
Yeah, I like the palm.
yeah, I did too. Force is almost kind of way.
Right here. This is it.
On the opposite side where the current is pointing, what direction is it gonna be?
Force, down.
Up.
Again,
We gotta keep that.
perpendicular to that plane. Now, what do we know about the nature of these two forces? Same length?
Now the thing's gonna start spinning.
Exactly. You've got two forces equal and opposite, so you're gonna have an equilibrium of force. But what you don't have is an equilibrium of torque. So if we were to draw a line down the center, each of these forces we could interpret as acting on a lever. Like this. I know, now we get to the map. We can deal with the map. And how would we calculate the torque for these forces?
2FL.
So to calculate the torque in general for a magnetic force, well, for any force, it would be L cross F, right? And we could write F as I
Oh.
L, not L in this case, but I times the length of this thing.
Times the magnetic.
Times the magnetic field. And the direction of this, well, we have to deal with that. But we have is there a cross product in it? In this part? I think there is, right?
There is.
You've got an L, you've got a B, or an L in the direction of I, and a B, and then the force is gonna be perpendicular. So you got something that looks like that. Where the length of the sides, I'll draw it again now, is this. And in a perfect world, I just make the lever half of that. So if we made this a nice square, then this distance, the lever, would be L over 2.
Is that what we're doing?
What's that?
Is that what we're doing? Is little L equal to
Might as
little
well.
L?
Yeah, so let's have the magnitude of little L be L over 2.
Since it's a couple, it is a couple, right?
What's that?
The two forces going like that, isn't it a couple?
Yeah.
It's a couple.
So you can just multiply it by big L.
By 2, or this is for the first segment, and then do it for the second segment, if you will. So this would be for 1, for the front segment, if you will. And then you would have IL cross B for the second segment, which would be in the back. Exactly. And what you're left with then is an expression, and this is sort of where it comes down. You've got your cosines, 90-degree angle, life works out maybe a little bit better. Once you know the direction of the force and the torque, if they're at 90-degree angles, if they're not, then you got to deal with that. But ultimately what you're left with is L squared over 2 B times the cosine of the angle if there is in fact an angle between them. Not a cosine, excuse me, the sine. The sine would be the angle between the force and L.
Sine is right, because it's gotta be 90 degrees and equal 1.
And this would be between L and FB. 90 degrees, so I'm not gonna have to not gonna worry about it, but, and then IL squared over 2, B sine L. Looks something like this. And the direction would be according to the right-hand rule again. So I'll just, this is the right-hand rule after you've used the right-hand rule, right? So you're constantly flicking directions. But ultimately, what it all reduces to, and I'll come back to that over there, is you're left with IL squared B, because the torques are additive. There are a couple. There's your 2, but the 2's cancel out. When we add them together, the 2's go away anyway. And then you do have the sine of the angle between the lever and FB. There's your area. Turns out if it wasn't a circle, then you could integrate it and you'd ultimately come to about the same conclusion. L squared is the area of the loop. Then you've got I, and then you've got B, and you've got the sine of this angle. Well, what does that reduce to? If you stare at it long enough, and of course you've got the I by the right-hand rule, what we're left with is that the magnetic torque ends up being describable by the relationship between this magnetic moment and the magnetic field. And so this is sort of a general statement when we talk about any magnet. Right? As long as they're fixed so that they rotate rather than just move in a magnetic field, they align themselves due to the magnetic torque interaction between the field of the two magnets, if you will, or between the magnetic field and the magnetic moment that's being affected. So it's just a way, kind of like with dipole moments, that you can write out potential in electric fields like a Coulomb's law sort of thing. Well, we can treat this magnetic moment to just sort of simplify all the other crap. If you know the magnetic moment for this thing, you just cross product with the magnetic field, that'll tell you the torque. So it makes life a little bit easier. But what it does mean, among other things, is that you can take any magnetic moment, which in this particular case might be a current carrying loop of wire, place it in a magnetic field, fix it so that it's capable of rotating. And if it's oriented the right way, not the wrong way, but if it's oriented the right way, you can generate torque and produce rotation. And the magnitude of that torque will be related to the magnetic moment, or if you will, the amount of current flowing through the wire. The area, because the area will represent the size of the perimeter of the wire that's being affected by the external magnetic field. And then ultimately the magnetic field. And this is the fundamental mechanism for an electric motor, which is one of the things that we'll look at today. So basically you have a magnet with a wrapped around coil of wire. Now when you have more than one wire, you have a coil of wire, then you just add an N here to account for the extra current, if you will. But placement, magnetic field, when the current is present, you can generate a motor from this, simple DC motor. So that's essentially the idea. Now what's kind of cool, if you can take an electric current in a magnetic field and produce a mechanical interaction, a torque, you can also, we talked about this with magnetic currents, or magnetic fields produced by torque. You can also take a mechanical interaction with a magnetic field in a loop of wire, run it backwards, and produce a generator. So, basis of our entire technology infrastructure, at least most of it, is the electrical generator. Well, what is it? It's basically a motor where you apply physical, mechanical effort to generate an electric current in a motor mechanism, basically. So it's basically torque run backwards. Apply torque to a magnetic field with a loop of wire, you generate a current. Or if you run a current through a wire in a magnetic field, you generate a torque. So there's a certain reciprocity of information there, or a process there. So to this end then, you can use a magnetic field to produce a current. And the way you do that is, first of all, you take your wire. Got to start with a wire of some kind. Doesn't have to be moving now necessarily. And this wire has a certain area. There's the area associated with the normal direction of the wire. And you put this in a magnetic field. Well, when you run a magnetic field through this thing, we can calculate a magnetic flux in here. So this idea of magnetic flux comes back into play. So, in a closed wire loop, it has to be closed because you have to have a way for charge to continuously flow and not get backed up on the ends. It can't just be a two-ended wire. But in a closed wire, we can calculate the magnetic flux through that wire when we apply a magnetic field. Well, that unto itself is, let's take a wire and put a magnet next to it, not much happens, right? Unless you have current, then you can generate a torque. If you don't, there's another way to do it. If you vary the flux with time, in other words, if we have a way of altering the magnetic flux in time, and this can be, by the way, varying the magnetic field in time, varying the surface area over this closed, over this patch. If you can somehow expand or vary the orientation between B